Okay, so in the case of a square root function, the domain is just non-negative. And wait a second, I'm gonna get out the conversation. Oppa. Yeah, and well, I'm gonna show you another example of where x has to be non-zero. So imagine, well, first of all, in here, certainly x has to be greater than 0, and that's it. And for a function like y equals 1 fraction 1 over x, here the domain of y will be, well, actually the equal sign is also not super correct, so the domain is such as, and here the domain is such as x is not equal to 0. So in here we cannot divide by 0, so when I was saying some stuff about convention, that's what I meant. So technically we can divide by 0. We all know that it's gonna be the infinite, right? But given the case of functions, we say, well, we have this function of 1 over x, we have to ask for x being non-negative. And the same actually will apply to y, it will be non-negative. So again, for the case of a square root, we can take a square root of 0, and that's why the domain, so all the values that x can take, can include 4, because if x is 4, then what? We have 0, square root of 0 is 0. If x, for example, is equal to 3, that's where we have a problem, because we'll have to take a square root of -1. If you know about the complex numbers, you understand that it's actually also not a big deal, but for our framework of functions, we say that if it is a square root, the domain is non-negative. That's how it is. Great, so for the logarithm, it has to be positive. For the fraction, it has to be non-zero. Okay, so we went through domain, we went through image, and then what's left on this slide is the range. So range of the function, here what I said is it's the set of all images. In other words, it's everything that y can be. And let's go back to our famous example of y square root of x minus 4. So here the range will be what? Okay, the same, just type it real quick. Okay, now I'm getting really confused and nervous about this example. Is it from minus infinite to plus infinite? Is it? Okay, no, let's go with this one. Okay, I agree with the second one, yeah. Okay. So, y equals to square root of x. So, how can it be minus infinite for y? It cannot, right? Okay, so I see now more answers supporting what I was thinking of. So y has to be greater or equal to 0. Okay, no, here for sure. Put plus, everyone who agrees that if x is equal to 4, then the square root of x is either 2 or minus 2. Okay, I have no pluses. Put minus if you disagree. Okay, I have one plus. Okay, only 2. Other options? Well, this is not even because it's a function. Something that is a square root of a is non-negative. Okay? Okay. This is, I hate these confusing moments because I really don't see your reaction. So the answer here is this. So y can only be something non-negative. And we consider square roots as non-negative functions. I understand where the confusion can come from. For example, we have y squared equals to 4. Then yes, if we are solving this equation, we are saying that y equals to 2 or y equals to minus 2. I understand that. But just a square root as a mathematical element, it has to be non-negative. So that's why it's much easier when you plot the graphs, and when you plot the square root of x, you are just in the positive quadrant. So here, again, that I'm positive, absolutely. I mean, last time I was also positive. But this is for sure that, yes, yes, please.
Am I audible?
Yes.
Yes. So if you assume y is equal to root x, that's also a parabolic function. If you just set aside economics and the first quadrant, it's a parabolic function which can be extended not only in the first quadrant, but if you plot the function, it goes to the fourth quadrant as well. Because for one value of x, we can get two values of y.
Okay, so what you don't agree with is this part, right?
I'm getting confused as to why x, as in my bone of contention is if x is equal to suppose a value, y will be the positive and the negative of the square root of that value.
Okay. What we're gonna go through is this. Let's plot it. Okay? Makes sense. I might. Okay, so what we need is x to the power of 1 over 2, right? And it is only the first quadrant. Because the square root is positive. So for the square root, it's just because we agreed on that. We agreed that square root of anything is just the positive part. Square root of 9 is 3. It's not both 3 and minus 3. Do you agree on that?
Thank you. Makes sense.
Okay, cool. So let's get here. We were here. So real value plots only, right? Yes, good. So we're all good, we're all set. For the revising of this part, you're gonna have this PDF with the correct options of here and here. Yeah, I know, if we're talking complex, then it all stops working, but now we're talking real numbers. And for y equals to square root of x, this is what we have, just because square root of 9 is only 3. And square root of 4 is only 2, and square root of 16 is only 4. Okay, perfect. So I erase this because it is confusing for later. Alright, so we checked off the main, image, and range. In the textbook, I think you also have that. And let's check something more of a blah 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 for a second. What are the examples of functions in economics? So here what I wrote is domain and range usually contain non-negative real numbers only. What do I mean by that? I mean that usually in economics we don't deal much with negatives. We cannot consume minus one apple, we cannot get I don't know, minus 1,000 euros to spend. Usually we talk the first quadrant. The first quadrant, I'll show you later what it means on the graph. Obviously, there can be examples of negatives. Utility can go to negative. If, for example, investment may be negative, if stocks, well, imagine stocks run down, so investment will be negative. There are. So that's why I put usually here. So we should mainly focus right on these non-negative real numbers. And here I have an example of a production function, which is also multivariable because we can have tools, physical force, labor, whatever. Put it inside the production function, pam pam pam, it does something, we get our output. So what are other examples of functions in economics? So just whatever you remember, where you've seen functions. Function of what? Cost function, utility function, yeah, TC is a total cost function. Budget constraint, after all, is also a function because we can express one in terms of another. We have, yeah, Cobb-Douglas is just a form of a function and it is either production or utility. Consumption function we might have. In macro, we have GDP as a function. We can have savings as a function of interest rate. We can have investment as a function. We can have a function expression for inflation. We can have the function as a dependency between Phillips curve, the one inflation versus unemployment. So tons of them, and everything will pass through the functions. So let's take a look at most common ones. So first we have our linear function, the sweetest, the simplest to deal with, the simplest to plot. You don't need any Wolfram alpha to plot that. You just need to come up with two, points on the plot, and here you go. So on the left side of my slide, you see that this function goes from minus infinity to plus infinity, as well as the second. But here, what I showed is all four parts of our graph. And this part, upper right is usually called first quadrant, this is second quadrant, this is third quadrant, and this is fourth quadrant. It is just to, you know, place yourself inside the graph, and it's not very crucial for you to know all the vocabulary about that. So left graph can be very well a graph of a utility function of one good. Like, for example, utility of consuming apples. Maybe it's increasing for us forever. The second option here that we have is the same linear function, but it is decreasing. And this reminds you, or maybe not, but give me an example of what this function can represent. Demand, yeah. The simplest way we plot demand is a decreasing linear function. Budget constraint we plot the same way, though our axis is more like one good, another good. Demand curve is the best example here. The best example here, because we have the value of demand, we have the price here and the value of demand. So it's different in economics. Usually in mathematics we plot independent variable x-axis, dependent variable y-axis. In economics we plot it the other way around, but that doesn't change anything, and the decreasing function will still be a decreasing function. Okay, cool. So again, don't get scared yet about plotting and everything. Most likely you will not have to plot anything except for indifference curves in this semester. Well, budget constraint too. Okay, cool. So this is our lines. Indifference curves, by the way, they can be also linear functions. Polynomial function. Polynomial function, like the left one, can be an example of a part, maybe, of supply curve, right? Like, if we only look at the positive quadrant, it will be, it looks like supply or marginal cost, something like that. And then the second graph that is here, I think I'm gonna use this equation somewhere again in my course. Yeah, I think so. But it's just another example, you know, of how a function can look. And you know, if it is x squared, what we get is a parabola. If we have anything cubic, what we get is this shape. It can be thicker, thinner, it can be moved to the left or to the right. Like here, for example, it does not pass through the origin, it's moved a little bit to the left. But that's the main shapes. So next, a square root function. And the square root function only is plotted in a positive quadrant, in the first quadrant. So remember that. This is, if some of you have seen a solo model, this is the thing. So any root, here I have square root, I can have cubic root, I can have fourth power root. It will always be like that. So here I plot, it will always be the positive quadrant. No, it will not always be the positive quadrant. A square root will always be a positive quadrant, and then the shape will always be like that. Okay, so for now, just picture that if you have square root of x or x to the power of 1 over 2, this is the picture. Cool. Then we can go to rational function. Left side, like this example, we can have that as a demand curve as well. The part that, the part that is in positive quadrant only, because here we don't have any demand. So this is also called the hyperbolic function. Maybe you've heard that. So this is the perfect rectangular hyperbola. We use it for demand, this part, but not this part. And this is another example of a polynomial function. So in general, rational function is a ratio of two polynomials. Polynomial is something with letters and numbers, let's say. It's an expression that we can write that contains our letters, for example, variables or parameters, and real numbers. Okay, so the right function, the function on your right, you will not see much, honestly. I don't know. This is weird, right? It can be, well, the part in the positive quadrant can be something expressing the growth in Solow model, but this one you will see. And what is going to be great about a function like that, if we're talking about demand, so demand function that is a hyperbolic has a constant elasticity of constant price elasticity. You'll see that also. Okay, cool. Exponent and logarithm. So here you can see that, for example, for exponent, the domain is everything and anything, so x can take whichever value, but the range is only positive numbers. Not even zero, only positive numbers. And for logarithm, it will be the other way around. So here the range is from minus infinite to plus infinite, but the domain is positive numbers only. So 0 is not included in this case because x cannot be equal to 0. Okay, convexity and concavity. That is, I cannot stress enough how important this can be. So write it down, print this slide and also hang it on the fridge and everywhere. So convexity and concavity are two concepts that are going to be used every day in microeconomics. And if you confuse them, you get everything wrong. So it's going to be very important for optimization. It's going to be important also for some parts of macro. But well, micro is where you're going to use this. And just remember that the left graph is convex and the right graph is concave. And I'm getting so excited about that because I know that every year there is 25% of students who confuse them and get minuses in points. So the way I remember what is concave is like, well, concave, you have a part cave in the word, and when you imagine cave, it's like this. You know, you enter in a cave, it's like that. So I hope it helps you to remember as well. But this is super crucial. Okay, you'll have this presentation. That's great. I sent it to you. So here you always have your cheating note of what is convex and what is concave. Okay. And now we get to inverse functions that you for sure heard and seen. but just maybe don't remember how to calculate. So let's start a new chapter, inverse functions here. Okay, great. So this unfortunately is also very important. Okay, an inverse function reverses an original function and it undoes what the original function does. Okay, so this we'll see it with the example because it's going to be much easier to understand, but just recall this notation. So if we have f that stands for a function, not just a letter f, but there was a function f that had its argument x, and we write this f to the power of minus 1 of x, we'll read it as f inverse of x. So f of x was the initial function, here is f inverse of x. And obviously by now you should be absolutely okay with the way how exponents work, and you know that anything to the power of minus 1 you just have to put the thing in the denominator, but not in this case. So in this case we should actually find an inverse of a function. So what I mean by that, you just have to remember that if initially you had y minus x, so you had this function y of x. See, now I'm using y instead of f here, and I can do it whichever letter. I prefer y, for example, right now. I can use y, and y to the power of minus 1 of x is not equal to 1 over x. Don't like very much writing stuff like that because for some reason it is remembered as is equal, but it is not. So let's do the red. Okay, it didn't work. Red. Okay, it worked. So here, it is not just putting the function to the power of minus 1. Okay, so how does it work? And first of all, how should we actually understand inverse? Well, it's quite simple. Like, for example, let's take y equals to x. So an inverse of this function would be y equals 1 over 2x. Why? Because 1 over 2x undoes multiplication by multiplication by 1 over 2 undoes what multiplication by 2 does. So if the correct way to actually write it would be this. Okay, so this is an example. Let's write that it's an example. If y of x is equal to 2x, then its inverse, so y to the power of minus 1, will be equal to 1 over 2x. Let's see. So that's the principle, and it's the easiest to understand on this simple example. Okay, so then we can check more complex examples where you cannot see straight what inverse did. So, for example, we are going to take this stuff and try to find an inverse. So, how to find an inverse of a function? we take an initial function. By the way, what is this function? Type me in the conversation. Yeah, it's Celsius, Fahrenheit to Celsius. So for those of you who are used to the US scale of Fahrenheit, well, here you'll have to convert it again and again and again. So that's the formula. Okay, nice. So the initial function is what? We just try to find Celsius given we already know Fahrenheit. Like, for example, here we can have a good option of train our image concept. So image of 451 degrees Fahrenheit is what? Okay, so if we just consider it as a function, we would say the image of 451 by the function is equal to what? Right? So in here, what I better say is straight. 451 is equal to how many Celsius? So what do? We do 451 minus 32 multiplied by 5/9. Sorry, up, here we go. Okay, well, we do the calculation, and I didn't do it, by the way, so I'm gonna do it with you. 451 minus 32 will be 419, right? Yeah, this is where I don't know how to do math. Am I right? Just put a plus if I'm right. Okay, cool. Thank you. Then can we divide 419 by 9? No, we cannot. So okay. So please do real quick with the calculator and type me an answer. Yeah, it might be. It might very well be 419 times 5 divided by 9. Yeah. So again, 151 equals to 232. Well, let's say times 78 Celsius. Okay, great. So perfect. Thank you very much. Thank you, everybody. Yeah, cool. So what we just did, we found an image of 451 by the function f. That's how we called it here on my slides. We called it function f. Okay, we found an image. Cool. That was just to train the images. Now, how do we find an inverse of this function? So, an inverse of this function will allow us to express Fahrenheit in Celsius. So, given we have something in Celsius, for example, for those of you who are used to Fahrenheit, you will be like, well, I can see the weather forecast saying 22, but what does it actually mean? So, that's why we need to find an inverse. So here, let's go step by step according to what I've written here. So initial function is put c instead of f. Okay, so that's what we get. Great. We put C, well, just because we know it can be any different letter, but it's just a nice way so you don't get confused. We put C because we know that it's going to be Celsius, and then express F in terms of C. So what we have to do is write the same equation, but the one that we obtained from here, not C equals to blah blah blah, but F equals to some function of C. Okay, so go ahead, do it now. And we're just gonna, wait a second. How many minutes you need? Okay, I'm gonna do it together with you, not looking at my notes, and we get back to it soon. And then if I have many pluses in conversation, we can go step by step. Okay, 3, 2, 1, let's go. Okay, managed. Maybe I made a mistake. So, okay. Wait, I had a question. Where did we get the 451 from? Yeah, it is just an example that I came up with. Let's use this Fahrenheit measure and figure out how much it will be in Celsius. Yeah, it's just an example. It's not an assumption. It's just example of one value that F can take. Why? Okay. You're right. Just that I don't get why I didn't. Okay, you're right. So it is exactly what you wrote. So let's do this conversion. Oh, or maybe not. Do you mind putting pluses if you didn't figure this conversion out? Like, how did these two guys get the expression of F? Okay, you got it, right? Cool. Sure. Everybody's sure. Okay, nice. Yes, so the inverse will be okay, I understand now. What was my problem? And here the inverse indeed will be F equals 5. Well, let's write it nice, like this. So it will be 9 over 5c plus 32. So now you know. Instead of Celsius, you can put wherever here, and you get Fahrenheit. So we can also write in the initial terms, so just to train the notation, f to the power of minus 1 of f is equal to that's how we will write it. Okay, so why do I use f again? Because, well, f was an argument of initial function, and we can write it like this, so it will be a pretty inverse. Or if we want to be very rigorous mathematically, we should write it like that. So this reads f inverse of f is equal to that. So we don't change the argument, technically we just change the form of the function. Okay, now I have a question for you. Well, first question is, can a function be its own inverse? And if it can, give me an example, please. Yes. Just the simplest, okay? Because I don't know y equals x. Yes, the simplest indeed. So when we want to inverse it, we'll get, well, something like x equals y. So yeah, it will be that. Another example that I can give you is y equals to minus x. For example, it's also going to be its own inverse. And even something slightly more complicated like this will also work. So let's here write it f of x is equal to minus x. Here f of x is equal to then f to the power of minus 1 of x, so an inverse, also equals minus x. And here, same, f to the power of minus 1, so an inverse of initial f is going to be our 1 over x. Okay, cool, great. That was the first question. Now the second question. Does any function have an inverse? So can I find, using my method that I wrote down on the slide, can I find an inverse of any function? Any existing function with real numbers? Correctly defined. Well, just make your guess. Okay, not every function has an inverse, that's right. Well, especially if I'm asking it like that. Then, which functions do have inverses? What should a function be like to have an inverse? Yeah, we for sure can find an inverse of a linear function, but not only. We can find like this one, right? The one that I wrote, the last one. It's not a linear function, but we still managed to find an inverse, and it's pretty. If a horizontal line intersects more than once. Okay, perfect. So that's to be said mathematically. The function can only have an inverse if it is a one-to-one mapping. What does it mean? So let's consider an example. I give you f of x equals x squared. So how would you go about this? If I just ask you to find an inverse, you maybe tell me that the inverse will be a square root of x, right? Because what undoes square? Square root undoes the square. But the issue here is exactly the same as we already discussed, that square root only switches to positives. So we lose one part of a function. And That's not the only example of a function that cannot have an inverse. So technically, yeah, we can say, well, if we want to undo squaring, what we should do is square rooting, but square rooting only results in two positives, and here we lose a big part. So we cannot do anything. We just say no, x squared does not have an inverse. And there are many more, and what unites them is that for every for any value of y, we can have two corresponding x's. It is still a function because for every x we have only one y. But so think of this thing, right? So see, for every x we have just one y, but there are y's, many of them, for which we have two x's. That is not one-to-one mapping, because if we want to make it one-to-one mapping, we have to take just one part of it, either left or right. Here we see that it is not one-to-one. The second, the concave version of a parabola, it is not one-to-one mapping. What else it's not? These two are one-to-one mappings. This one is not one-to-one because, for example, for the value of the function minus 0.6, we have two arguments possible. Here, it is one-to-one mapping, see? So for each x we have one y, and for each y we have one x. And this is a nice, maybe you find it also as me, easy explanation that Walid provided us. A horizontal line intersects more than once. So imagine here you see this function. Imagine you put here a horizontal line on the level of 6, for example. So how many times that is intersect the graph? Twice. Okay, already not working. So here, for example, we put a line and we have only one intersection. That's working. So this is one way to memorize it. Another way to understand that for every y we should have only one x, and this is a function that we call one-to-one mapping. Okay, so only the functions that are one-to-one mappings have an inverse. Okay, great. So now we remember that. So if I give you something that is not one-to-one, you will tell me this function does not have an inverse. Cool. Well, I'll see how I arrange these notes when we're finished. Then, okay, we replied to all questions about inverse functions. And why do I want to spend so much time here? Because we're gonna spend also a lot of time on how to calculate a derivative of an inverse function, and inverse functions are gonna be involved into a couple of important theorems in micro. So to understand the theorems, you should understand how, well, first of all, what is the concept and how does it work and how do we find it and calculate it. Okay, well, you can make a little note for yourself of inverses of the most common functions, but it's really useless because we're not gonna actually go ahead and ask you, oh, find an inverse of this weird function. You just have to know how to do it, because it might appear as a part of a proof of a theorem, for example. or you just might need it to prove your point, or for something. So you have to know how to find inverses, and you have to understand that not every function has it, and that there are some functions that are their own inverses. Okay, cool. So inverse function graphs. That's very interesting. And I promised yesterday that I'm going to show you something beautiful about exponent and logarithm. This is, well, something cool to know. A function and its own inverse are reflected over the line 1 equals x. So if you have a graph and you put the 45 degrees line, which is 1 equals x, you're gonna have a symmetrical graphs of inverse functions. Why and where can you use it? Well, imagine you have to find an inverse for some reason. You just need the expression. And you're like, okay, I found it. And then how do you know that it's a good one? You can do the Wolfram plotting, like here. Oh, on this website. I think you all know it. You should all know it. If you don't know it by now, just write down real quick Wolfram Alpha. You're gonna use it for everything. And plot them both and see, are they symmetrical or no? Well, if they are, then they are most likely the inverses. Great. So, functions of two and more variables in economics. So someone mentioned Cobb-Douglas function to me. This is how it looks. So first of all, what is the most common example of two or more variables function? I could think of a production function and utility function. Well, these are the two that for sure have more than one variable, because, well, we don't only produce using labor, we produce using both in very, very, very simple models, like in sum of macro, where the whole thing is too complicated that we don't want to really deal with many variables. We can say, well, let's assume we only use labor. But in general, and you understand that real life doesn't work like that, to produce something we need a bunch of stuff. So it's not only capital and labor, it can also be energy as the third component here. That's a very famous and popular recently way to write down a production function, because we're all environmental friendly. So we're gonna say, well, energy component is very crucial, and the less energy we consume, the better, and blah, blah, blah. So you can have here not only 2, but 5, 6, 7, infinite, whatever you use in your production. For the simplification, we might use 1, but usually, and in economic growth exactly, you will always have 2 of them. You will always have capital and labor. If you've done economic growth already, you know that you can have a technology factor there, but it's usually not a variable, it's something exogenous. Okay, great. So Cobb-Douglas function. Here you can see it here, and you can also see it here, and you're like, what is that? So a Cobb-Douglas function, you can have a coefficient, but the main thing is that it's a product of 2 of your variables, or 3. You can also have 3. So product of your variables raised to some powers. So here I just have alpha and beta. I have this coefficient A, which is that very technology factor in economic growth. So alpha and beta, they are whichever exponents. 2, 3, whatever. A particular case of Cobb-Douglas is when they sum up to 1. So for example, alpha is 1/3 and beta is 2/3. And that's the most common function that you're gonna use too. So get used to this notation, and it's sweet because for derivation it's comes up to really pretty expressions. So this function is called Cobb-Douglas, and the characteristics are a product of variables raised to powers with a coefficient or without coefficient. Then utility function, another example. Here I wrote utility of many. Actually, in case of utility function, you will for sure see a function of 3 variables. 4, will you see 4? Maybe. And here the Cobb-Douglas function, this is a classics of your microeconometrics. So you're gonna meet your professor, Angelo Secchi, and you're gonna fall in love with him. He's really great and very motivated when he explains, and you can see that he likes teaching and he likes his job. And it's gonna be a very interesting class, but also very challenging in terms of math, and you have to follow, and he's really, he needs you to understand the whole math thing. So his favorite utility function is a utility of a consumer who lives on Ferraris, so it's F, and baguettes, which is B. In standard economics, we usually use two goods utility function, and Secchi's favorite is Ferrari and baguette. And here you can see that we have 1/2 and 1/2. So they sum up to 1. This is the best, sweetest Cobb-Douglas function that is nice to find the derivative of. You'll get to it. Okay, then minimum function. Very important. If you didn't see it, here it is. I'm gonna give examples, I think, here, no? Yes. So I need to explain how it works, but this is a perfect representation of a utility function. Do you know in which case? Does someone know when we use min functions? In case of utility, especially. Not, well, when we have our goods that are perfect substitutes. Exactly. Left and right shoes. We can have coffee and croissant that we only consume together and never separate. Minimum function is something that is about perfect complement. So we have two goods that we always consume together. Like, for example, for each 2 croissants, we consume 1 cup of coffee. That's the framework, and sounds quite realistic. Or for every 1 croissant, 1 cup of coffee, or 1 croissant, 2 cups of coffee. Depends on your preferences, because all utility functions, after all, depend on your preferences.